Hey guys, this is Megan again from OnlineMathCircle AIME video tutorials, and today we are going to look at 2009 AIME I, problem number 11. Consider the set of all triangles OPQ where O is the origin and P and Q are distinct points in the plane with non-negative integer coordinates x, y, such that 41x plus y is equal to 2009. Find the number of such distinct triangles whose area is a positive integer. So, first of all, we have to identify the coordinates O, P, and Q. First, we know that O is the origin, so O is just 0, 0. P and Q are distinct points in the plane such that 41x plus y is equal to 2009. So if we want to write y in terms of x, we can subtract 41x from both sides, and that gives us y equal to 2009 minus 41x. And then basically, if we let p be equal to x1, y1, and q be equal to x2, y2, in order to uniquely identify these points, we can write all the y terms in terms of the x terms. And by doing so, we get P equal to x1 2009 minus 41x1 and point Q as x2 2009 minus 41x2. So now we have to find the number of such distinct triangles whose area is a positive integer. So let's try to compute the area of triangle OPQ. So we're given 3 points in the coordinate plane that identify the vertices of OPQ. And there's a special formula that we can use whenever we're given 3 distinct vertices of a triangle and we're asked to find its area. This method is known as the shoelace theorem. And you'll see how it got its name in just a moment. So, in case if any of you are new to this, the shoelace theorem is a special method where we can find the area of a triangle in a coordinate plane given 3 points, x1, y1, x2, y2, and x3, y3, none of which are collinear to each other. So, in order to do this, let's start out by writing the points coordinates in 2 columns, the x column and the y column. So we have x1 and y1, x2 and y2, x3 and y3. And next we want to write x1, y1 again at the bottom. Now what we do is we draw diagonals from each of the points on the left-hand side to the point diagonally below it on the right-hand side. So we connect x1 to y2, x2 to y3, and x3 to y1. And we take the sum of all the corresponding products there, and that gives us x1, y2 plus x2, y3 plus x3, y1. Then we do the same for all the points going diagonally upward. So we have these. And you'll notice how when we cross those points, it looks almost like a shoelace being tied. So doing the same thing here gives us x2, y1 plus x3, y2 plus x1, y3. And then the area of this triangle would simply be just 1/2 times the absolute value of the difference between these two sums. So when we write it out, we get the following. X2, y1 plus x3, y2 plus x1, y3. And we get the formula for the area of a triangle using the shoelace theorem right here. So, returning back to the previous problem, let's try the shoelace theorem for these 3 points. So, how do we do this? Well, we first list them in columns. We have O here, then we have P, and then we have Q. And then we write down point O again. Then we compute the diagonal products and sum them. So 0 times 2009 minus 41x1 is obviously 0, plus x1 times quantity 2009 minus 41x2 plus x2 times 0, which is 0. So that gives us x1 times 2009 minus 41x2. Now, we do the same thing for the upward diagonals, from left to right. And we create our shoelace. And x1 times 0 is 0. x2 times 2009 minus 41x1 plus 0 times 2009 minus 41x2, then that's 0. And simplifying that gives us x2 times the quantity 2009 minus 41x1. Now, the area of triangle OPQ, by plugging into this formula here, gives us 1/2 times the absolute value of x1 times 2009 minus 41x2 minus x2 times the quantity 2009 minus 41x1. And let's simplify that. So expanding that out, we have 2009 x1 minus 41 x1 x2 minus 2009 x2 plus 41 x1 x2. So the x1 x2 terms cancel out. And we can factor out 2009 out of the absolute value sign. So the area in terms of x1 and x2 would be 2009 over 2 times the absolute value of x1 minus x2. Now, we need to find the number of such distinct triangles OPQ whose area is a positive integer, as stated in the original problem statement. So in order for the area to be an integer, we need to have the absolute value of x1 minus x2 be divisible by 2. And basically, in order to accomplish this, x1 and x2 must have the same parity. In other words, they need to be either both odd or both even. And we also have the fact that because of the fact that 41x plus y is equal to 2009, and we must have non-negative integer coordinates xy, we have the restriction that x1 and x2 must be between 0 and 49 inclusive, since we have 49, 0 as the x-intercept of the line 41x plus y equals 2009. And since P and Q's coordinates can be permutated, we have the total number of distinct triangles as 25 times 24, which is equal to 600 triangles total.